Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about some basic derivative rules, and ladies and gentlemen, it's time. It's time to say goodbye to our friend, the limit definition of a derivative. I wanted to start this video by giving the limit definition of a derivative a little bit of a tribute. We thank you, limit definition of a derivative, for helping us find instantaneous rates of change, as well as slopes of tangent lines, providing a means for us to do so will never be forgotten. Godspeed, my friend. Well, actually, we're going to still need it to prove some of this stuff, especially when we get to the quotient and product rules later, but we're no longer going to be using the limit definition to find some derivatives. And that's what the point of this video is. A lot of these first few rules we're going to get for free, quote unquote, just by limit laws, since a derivative is still a limit. So let's see what they are. Here you go. You've got the derivative of a constant, which says that if you take the derivative of just c, where c is a constant, that's just 0. You've got a constant multiple rule, where if you're taking the derivative of c times some function, you can bring out the c, and those are fairly straightforward, again, just from limit laws. You've got the sum and difference rule, which say if you take the derivative of a sum, it's just the sum of the derivatives, and if you take the derivative of a difference, it's just the difference between the derivatives. And at this point you might be thinking, I mean, that's great, but how does this really help us, right? You still have to find the derivative of whatever f and g are, and these don't help us bypass, the limit definition of a derivative. Well, check this out. This is the power rule. It says that if you take the derivative of x to the n, that is actually just n times x to the n minus 1. And this is true for any real number n. By the way, I'm not going to prove these things, at least in this video. Maybe I'll do a separate video that proves perhaps the power rule. So for now, you're just going to have to take my word for it. We've done plenty of examples before where we're looking at derivatives of like x to the fourth and x cubed and stuff like that, and should have started seeing a pattern where the power was just decreasing by 1, and whatever was the power ended up getting multiplied by whatever the coefficient for that monomial was. But yeah, that's the thing. Power rule, super useful, especially for taking the derivatives of polynomial stuff. Let's do an example. All right, number 1, find the local minimums and maximums of p of x is equal to this quartic polynomial function. Finding mins and maxes means we need to figure out where the derivative is 0. So let's find the derivative first. If you're going to take the derivative of p of x, taking the derivative of x to the fourth minus 6x squared plus 4, I'm going to take this in steps just based on the rules that we had, but soon you're going to be able to just take the derivative. You could go from here directly to what p prime is. But let's break it down. First, we're breaking it down with the sum and the difference rule. The derivative of a sum and difference is just the sum and difference of its derivatives. So that's what we've done here. Next, I went ahead and I used the power rule on this part. Bringing down the 4, that was the power, and now we're subtracting 1 away from that power. I used the constant multiple law here to bring out the 6, and we're going to eventually use the power rule. In our very next step, we'll use the power rule on here as well. And then we had the derivative of a constant, and that was just 0. Okay, so going one more step, bringing down the power for 2, using the power rule. For that second term, we'd have 2x to the first. That 6 is still being multiplied out in front, and so we end up getting that the derivative is 4x cubed minus 12x. See how fast that is? No need to use the limit definition with these kind of abbreviated techniques. So we know, right? We know p prime is 4x cubed minus 12x. We still need to figure out what the minimums and maximums are. So we should figure out where is this polynomial 0. Where the derivative is 0 is going to correlate to some local extrema for the p function, for the base function. So I went ahead and I factored it into 4x times x squared minus 3. And then I figured out that, okay, well, if this is equal to 0, I can use the 0 factor property on it. And I can come up with x is equal to 0 from this equation, or x is equal to plus or minus 3. That's where p of x is going to have its x-intercepts. So I'm trying to figure out, now I know where the extrema take place. They take place at 0, at negative root 3, and at positive root 3. But I still need to assess which of those is minimums and which of those is maximums. So I need to make some kind of a chart that helps me figure out where is the graph positive and where is the graph negative, since that's going to help us assess local minimums and maximums. Well, in this particular example, since I know the leading coefficient for this thing is positive, and I know its degree is odd, that tells me something about the end behavior of this polynomial function, right? This is kind of a pre-calculus concept. We're looking at end behavior, and all that relies on is leading coefficient and the degree of the polynomial. If it's an odd degree with a positive leading coefficient, that means that the function will be rising on the right and falling on the left. And if it's supposed to intersect the x-axis at these specific points and also fall on the left and rise on the right, then I would posit there's only one real possible way to draw this particular graph, and it would be like this. Right? There'd be no other way for this thing to intersect the graph in 3 ways, right? 3 times, which by the way is the maximum number of x-intercepts that a cubic function can have, and then also fall to the left and rise to the right. So this is it. So we know it's negative in this interval, positive in this interval, negative in this interval, and positive in this interval. Now, if you're not familiar with end behavior stuff and you're not real confident on being able to graph the function, you could perform a sign analysis, which we've talked about before in a previous video. But the point is, in the interval negative infinity to negative root 3, the function's negative. In the interval negative root 3 to 0, it's positive. 0 to root 3 is negative, and root 3 to infinity is positive. And so now we can assess where do some local maximums happen. Where the graph goes from positive to negative, that's a local maximum. So there's a maximum at 0. Where the graph goes from negative slope to positive slope, that's going to be a minimum. So this thing has 2 minimums. It's at negative root 3 and at positive root 3. And this, by the way, we've talked about before in the last video that I did about what does f prime say about f. We figured this stuff out. Oftentimes this is referred to as the first derivative test, which is something that we're going to talk about a little bit later. Now, we know where the maximums and minimums happen, but if we want to figure out what they are, we have to plug these values into our original function so that we know what the coordinate is, what the high point is, what the low points are. So I went ahead and I did that. You can check my math here. But the moral of the story here is that P has a local max at the coordinates 0, 4, and P has 2 local minimums. One of them's at negative root 3, negative 5, and the other one's at root 3, negative 5. All right, and those pertain to this function. This is going to come into play when we start doing some optimization sort of stuff. Finding where the derivative is 0 helps us figure out some extrema. And now we have a shorter way to find the derivative for polynomials. Hey, here's a cool fact about the slope of y is equal to e to the x at x is equal to 0. It's 1. The limit as h approaches 0 of e to the 0 plus h minus e to the 0 over h, which is equal to this thing here, is just 1. Evidence the graph. For justification, I'm just going to use the graph of e to the x minus 1 over x in this case, which you can clearly see has a limit of 1 at 0. Now, why is this so cool? Well, it gives us the derivative of e to the x, which is e to the x, which is pretty cool. Here's the proof if you want to pause the video and check it out. But the point is the derivative of e to the x is actually just e to the x. E to the x models its own slope. How cool is that? Here's an example. Let's figure out where f of x is increasing here. It's defined to be 5x minus e to the x. We want to know where it's increasing, which means we need to know where its derivative is positive, so we need to take the derivative. If you take the derivative of 5x minus e to the x, first thing you do is apply the difference rule for it. So we're taking the derivative of 5x minus the derivative of e to the x. The derivative of e to the x is just e to the x. The derivative of 5x, we can first use the constant multiple rule to bring out the 5 in front of the derivative of x. But the derivative of x is 1 times x to the 0. Its power is technically 1. So the way that I like to think about it, using the, if you're differentiating, we're differentiating this thing. If you're going to use the power rule, the 1 gets put down in front. You multiply that by x, and you raise it to the 1 minus 1, which is 1x to the 0. But x to the 0 is just 1. So this is 1 times 5, which is 5. So here's our derivative. Now we want to figure out where this is positive because we need to know where 5x minus e to the x is increasing. That's where its derivative is going to be positive. So let's just set this thing greater than 0 and solve. First thing I'll do is I'll add e to the x to both sides. To undo the exponentiation of e here, we'll take the natural log of both sides. The natural log of e to the x is just x. So as long as x is bigger than the natural log of 5, and I don't know what that is, it's something less than 2, I think. But in any case, f of x is increasing on the interval negative infinity to the natural log of 5. So that's it. Pretty short video today. Just wanted to go through the power rule mostly, and show you guys that the derivative of e to the x is e to the x. So thank you guys. Hope you learned something. If you have any questions, send me an email or drop a comment below. Thanks a ton for watching, and I'll see you in the next one.